Our next big tool for working with square roots is the product rule. There's nothing new here. This is just a special case of our rule for putting an exponent over a multiple base. So for square root, here we have exponent 1/2, and so that's going to be AB to the 1/2 is A to the 1/2, B to the 1/2, and then we just take those 1/2s, go to square roots. So the square root of AB is the square root of A times the square root of B. There's nothing special about 1/2 here, so if I replace it with 1 over n, then it's the same rule for nth roots. We just have to remember that the n's will have to match to use the rule. Before we go to examples, let's take a look at two special cases of square root rules that we're going to use often here and beyond this video also. First, if I take the square root of a square, we can think of that as just canceling out. So if you got a square inside of a square root or an item next to itself in a square root, then you can think of that as moving it outside the square root like so. Second rule, well, that's just what it says. Square root of a thing times itself gives us the thing on the inside, or taking the square of a square root gives us what's on the inside. So squaring and square root cancel out in either order. To see these, if we use rational exponents, then these are just given by these statements here. So I take x squared to the 1/2, we get x to the 1, which is x. And if I take x to the 1/2 times x to the 1/2, we get x to the 1 again, which is still x. So these, not too difficult to dig yourself out of if you're not sure of how they go. Now, numerical examples. So first one, if I take square root of 2 times square root of 3, we put them together, we get a square root of 6. This feels like symbol pushing, but actually remember, we can approximate these numbers. So the square root of 2, 1.414, and so on. Square root of 3, 1.732, and so on. If we multiply these together, we get what we expect for the square root of 6, say from our calculator. So this is consistent numerically. For an example with the cubic, we won't worry about the approximations. If I was to take cube root of 7 times cube root of 9, we just put it together, cube root of 63. So up to here, it doesn't really seem like there's much going on. Where this is going to mean for us, well, there's this business of simplification of radicals. What we're going to want in our square roots, if there are squares inside of our square roots, we want to move them to the outside per the rules we talked about on the other side. Same idea for nth roots. For nth roots, we don't want nth powers under our nth root. What's the reason for this? Well, what can happen if the whole class goes and does the algebra for a problem? If we're not simplified, people can get answers that could be all correct but look completely different. So when we simplify, the rule for simplification puts everyone on a common language where if everybody followed the simplification, all those correct answers should look exactly alike. Let's take a look at an example. So for instance, if I have square root of 200, okay, now if I stop and think about this, the biggest square I could find that divides into 200 is going to be 100, which is 10 squared. So I'll split off the 100. You could use the rule to write it out as 2 square roots, and then that's going to give you 10 square root of 2. Okay, more often than not, you'll just see the 100 and bring it out in front. It's worth reminding you that we should check our work, okay, and we got the rule now to help us check that. If I take this square root and multiply it by itself, so 10 square root of 2, 10 square root of 2, we do the work. The 10s give me 100. I've got a square root of 2 times square root of 2. So that's a square root of 2 by itself, which is going to go to 2 by our rule over here. And so that's going to give me the 200, which matches what's under the radical. So that's totally legit. For our next example, consider the square root of 48. Here, the biggest square that divides 48 is going to be 16. Okay, we have 3 times 16. we take the square root. We can either split it up into 2 square roots, or I think of it as I'm going to take the 16 and pull it out in front by its square root, which is a 4. So 4 square root of 3. For a cube root example, here we don't pull out squares. I want to pull out instead third powers. So for instance, if I had the cube root of 54, the biggest cube that goes into 54 is going to be 27. Okay, 2 times 27. And again, all we'll do, the 27 is going to come out by its cube root. So that's going to give me 3, and then what's left over is cube root of 2. Now, let's work some variables into our square roots. So to start slow, let's try the square root of 50x squared y. I'm looking for the biggest square that divides each term. So 25 will be the biggest one that goes into 50, 2 times 25. X squared is a square itself, and y is as is. So we'll pull 25 out as a 5. X squared comes out as an x, leaving us with a square root of 2y. If this answer seems unlikely, we can always check as usual. I'll just take our answer, multiply it by itself, and make sure what comes back is what's under the original radical. So if we do this, okay, 5x and 5x gives us 25x squared. I've got radical 2y times itself, and so remember our rule is just throw away the radical. So that gives us a 2y, and that gives us 50x squared y, as expected. Now, with variables, we may need to deal with larger powers. So if you want a general rule for that, if I have a square root of x to an even power, we just cut that even power in half. Okay, and the way to think of that is if I've got x to the even, that'll break into x to the half times x to the half, and so we use our rule from before. If I have an odd, what we'll do is we'll split off an x to the 1. Okay, if I take 1 off of an odd number, I get an even number, and then we just use the rule from before. So that's going to give us a square root of x factor left over. Now, for an example where things go cleanly, let's try square root of x to the 4, y to the 6. Rather than going directly to the rule, let's show you the mechanism of the rule. So what we'll do is, I'm going to split the x to the 4 into 2 parts, x squared, x squared. Okay, they add the 4 by our product rule. And then the same thing for the y to the 6. It gives me a y3, y3. These occur next to themselves, so they just come right out as is. So x squared and y cubed, and then that's our answer. So the radical goes away completely. Of course, we check our work, so we'll multiply this by itself. And then product rule is just collecting the exponents, adding them together to get our x to the 4, y to the 6 as promised. Now let's try an example with an odd power. So I'll have square root of x to the 7, y to the 6. If I take half of 7, that's not going to go cleanly. So what we'll do instead, I'll take off 1x from the x to the 7. That'll leave us with an x to the 6. And now the x to the 6 goes to an x cubed. The y to the 12 goes to a y to the 6. And what we're left with under the radical is an x. So we get x cubed y6 square root of x. If that looks strange, we could always check our answer. So we'll take our answer and multiply it by itself. X cubed goes to x to the 6. Y6 goes to y to the 12. Square root of x. We noted from before is just x, and so the x to the 7 comes out as promised, and so we match, and that checks our work. If we want to do this technique with cubes or higher powers, we got to think a little bit more. So I'm going to label this as hard. It's kind of difficult to get by just watching someone do it, so you'll have to sit down and work examples until you get the hang of what's going on. But I'll do my best shot here. Now, as a warm-up, let's go back to the last video. Suppose I want to take the cube root of y to the 15. Well, if I put this in rational exponent form, we got y to the 15 to the 1/3. 15 over 3 is a 5, and I get the clean answer of y to the 5th. Now, say we consider this example, cube root of 32, x to the 8, y to the 16. If we put the 16 over a 3, it's not going to go evenly, but I know the 15 will give us something clean because it's a multiple of 3. So what I'll do is we'll split off a 1 like before, y to the 15 times y. And I'll have to take a look at the other terms also to see what the biggest cubes that we can pull out are. So for the 32, we can pull out an 8. For x to the 8, okay, we know, well, if I put 8 over 3, it doesn't divide evenly. And x to the 7, not divisible by 3. X to the 6 is, though. So if I want to use x to the 6, I got to think about what's left over. That's going to be x squared. Now I've broken things down into all the pieces that I can use. So the 8, cube root of 8 comes out as a 2. Cube root of x to the 6 comes out as x squared. And we saw y to the 15, cube root is going to come out as y to the 5th. What's left over just gets collected underneath the cube root, so that'll be cube root of 4x squared y. And then that's our answer. Note, if we don't believe it, we could go and check that. Okay, we'll multiply our answer by itself. We've got 3 times, but we're not going to do that here. To finish, let's take a look at what we really want this rule for, besides simplification, is also when I multiply square roots together, even if the things we start off with are simplified, the answer might not be. So for instance, if I take square root of 21 times square root of 3, there are no squares in either of those. We multiply, we get square root of 63, which is now divisible by 9. So I can pull the 9 out, get a 3, and then we got 3 square root of 7. So that's based on the technique that we've been doing. With cube roots, same idea. We can take our example here, 3 cube root of 4, 4 times cube root of 6. We use our product rule to combine the cube roots. So that'll give us a 12 cube root of 24. 24, the largest cube that divides that, is an 8. I could pull that out as a 2, and we get 24 cube root of 3 as our answer. Finally, let's try one of these with a variable in it. So I'll take square root of 2x times square root of 14x. Note, no squares in either of these. We multiply, we use the product rule. I get 28x squared under the square root. Largest squared in there, we got a 4 comes out as a 2. The x squared comes out as x, leaving us with square root of 7. And then we get our answer. And of course, we could check this if we wanted, but we'll leave it there.